Cool. Okay, we're going to go through the first year AI1 paper, the Resit one from 2022. Cool. Question one was clustering. I think this is the same as the one that was on our mock, I'm not sure. But use hierarchical agglomerative clustering with complete linkage to cluster a one-dimensional dataset with the following points. And then we have these points. And we want to show the step-by-step calculation of how we're forming those clusters. If there's a tie, we select the first pair from the left to right. Draw the resulting dendrogram with heights on one side. Assume that we want to cluster this dataset into three clusters. Which three clusters would the dendrogram give us? Okay, let's start with this question. Yep, it's the same. Part B isn't. Oh, right. Okay. Yeah. Okay. Well, we'll start with part one anyway. Part A. Actually, let me get the question one as well. Okay, so I mean, how I'd do this, I think I did get it a bit wrong in my solution, so I'm just going to draw it out again. So we'd sort of have everything would be in a cluster by itself initially. And then we'd compute the distances between those two. We've been told you want to use complete linkage, so what does complete linkage mean? Maximum, yeah. So the maximum distance between any 2 points in the two clusters. Initially, everything is just in a cluster by itself. So there's only one distance we're really looking at. So the maximum of that one distance is just that distance. So it's just the difference between the two numbers initially as the complete linkage values. So,
Yes.
hey, okay. So all of these would just be 0 because it's a normal distance metric. 3, 7, 4, 5, 8, 14, 22, 23, 24, 1, 4, 10, 18, 20. Let me know if I'm getting any of this wrong. 19, 11, 9, 8, 6, 14, 19, 16, 17, 18, 19, 20, hey, 21, 2, 3, 4, 5, 8, 10, 2. Okay, so what we'd do first is what are the first two we'd merge in this case? Or what are the first two sort of clusters we'd put together? 7 and 8. Good, yeah, so this 1 is the smallest value. That's not any of these 0. So this 1, we'd merge this 7 and 8 into one cluster. So 7 and 8, and we merge it at a height of 1. Okay. I'm just going to draw this out again, just so we can see exactly what's going on. So we've merged that 7 and 8. Now, these two become one cluster, essentially. So now we have... Now our table looks something like this. That is not the best way of writing it out, but... we're essentially merging those two into one. So now we have 7 and 8 in its own cluster. And we look at the maximum distance. So here we'd put 5 because it's between... or actually we'll do it in these. Okay, so here we'd put 5 because 3 and 7 is 4, 3 and 8 is 5. I'd probably recommend drawing multiple tables. In the mock scheme, did they just use one table? They didn't even do the table. Oh. That's strange. Okay, so now we have something like this. No tables, just clusters, then calculate distance and merge. Right, okay. I guess you don't have to draw the table out, but I always find drawing out the table helps me see exactly what it is I'm merging and what all of the different CL values are. So I'd highly recommend it, just so that the examiner as well can see your step-by-step working, exactly what you're doing. Okay, so here, oh my god, I can't draw a straight line. Okay, 0, 0, 0, 0, 0, and then we'd have our differences here. So the maximum difference would be 10. Between 11 and 17, we've got 6, then 16, then 14, 10, 4, 8, 5. That looks about right. And then in this case, we'd look at this 4, so we'd measure 7, 8, and 11 at height 4. And it looks like Adwit sent his solution, so let's just take a look at this. Actually, let me finish this and see if we get the same result. So now we match 7, 8, and 11. So now we have 3, 7, 8, 11, 17, 25, 27. And we have 3, 7, 8, 11, 17, 25, 27. Boom. And even if it might seem like you're drawing a lot of tables, the tables do get a lot smaller every time, so it's not really that bad. 3, 7, 8, 11, 8. 3, 17, 16, 15, 14, 24, 7, 8, 11, 20, 10, 10. Does that look right? That looks about right. Then we merge this, so 3, 7, 8, 11 at 8. And then we merge, so we've merged these two now. I'll just draw it out again. Okay. 3, 7, 8, 11, 17, 25, 27. 3, 7, 8, 11, 17, 25, 27. Are these steps sort of making sense to everyone, what I'm doing here? How I'm merging them and deciding which ones to merge together. 3, 7, 8, 11 at 17 is 14. Yes, what would you do if the lowest distance is joint same? Yeah, so they said just like always measure one on the left first if there's two that are the same. In this example, I don't think we have any two that are the same, but yeah, that's what you'd do in that case. So here we merge these, so 17, 25, 27 at 10. And hopefully we can all see that after we merge 17, 25, 27 at 10, we just have 3, 7, 8, 11, and we have 25, 27. And we're going to merge these two. At what height will we merge these two? So if we put in these heights, I believe this one should be 24. We'd merge these two at 24. So 3, 7, 8, 11, 25, 27 at 24. Okay, so these are the series of merges we take to group all of this data, and we've done this with, we've used agglomerative clustering to take these steps. 24, cool. Okay, and then part II is to draw the resulting dendrogram from this data. You've missed out 17 in the... Oh, you're right, yeah. So we merged 17 here, didn't we? Good spot. Cool. Right. So yeah, that's part I. Let me move this to there. And then for part II, we sort of just want to draw the dendrogram. So our dendrogram would go up to, let's say 24. Might start 0 and go up in 2s or whatnot. And then across here, we'd have all of our data points. And the y-axis would be okay, how am I going to do this? Right, and the y-axis would be height. The height at which we merge those two things. So what I'd say is let's choose a smallest value. So 7 and 8, they're merged at 1. I'll bring this down actually as well. Okay, so 7 and 8. We merge these two at 1. If this isn't to scale, hopefully you guys do get the idea. That's at 1. And then 25 and 27 we do at 2, so that's somewhere here. And then 7, 8, and 11. So we add 11 to this 7 and... Ooh, actually, I don't think we should draw it like this. We should probably do one sort of cluster at a time. So 7, 8, then we add 11 at 4. One sec. Why not? Yeah, only thing is if we draw it in order, we kind of have like a cross like this. And I mean, it's sort of, based on all the dendrograms I've seen, it's kind of conventional to ignore that. Like to not have a cross in the middle of the dendrogram. Because if we then did something like, if we did do it like that and then said 25, 27, and then we did 11 here, then this would come here, and then this would cross through here.
As in, how are you deciding what order to do it then in? Are you just trying to like visually see right now? Because in the in just ascending order of values, there are no crosses in the dendrogram in this case.
If we just do it in ascending order?
Yeah, there are no crosses. So you have to start with 3 firstly.
I guess that would work in this case if we just do it in the...
Yeah, so you need to put 3 before 7. Then...
Yeah, I mean, it would still work if we did it after, because that's the last one, so that's like 24, but... Yeah, I see what you mean.
How would you decide which way to do it? Is it just like anything that doesn't involve a cross?
Yeah, I feel like it's just... I don't know what the systematic way to do it.
I don't know if they'd penalize you if you did it in order of values.
I mean, generally you can do it in the order in which they actually merge.
Yeah.
So for this one, 7, then 8, then 11, then 3. And you can do 25.
Why 7 before 3?
20... Because that's the...
I mean, it's up to you, but that's what we started with.
Oh, you're doing it in the order of merges. Okay.
So that's... It
shouldn't really matter, to be honest.
Yeah.
Oh, so order of merges would work every single time, right?
I think so. Like, if you did it like that, where you add one by one to this cluster. So then we add 3 at 8. This is definitely not to scale.
Fine, you're doing logarithmic scale. Okay, that makes sense. Yeah, actually. Wait, that would be a better solution then. That way you end up with like dominoes sort of thing, and there'd be no crosses. Fair enough.
What's that? That's 2. Oh, that scale kind of worked out.
Obviously I did the axis, but I just wrote like the number it corresponds to, like in small, on top of the line to like indicate where it's going to.
Yeah, I guess that could work. But yeah, your dendrogram should look something like this, which Kevin's also got something quite similar to that.
Yeah, so what Kevin did, I did the same thing as Kevin, which is like, it's correct.
Right, but yeah, so that would work.
With this approach, the one that we did, Kevin, is that you might lead to crosses and like intersections, which would lead to ambiguity in the dendrogram, because a cross and like an intersection generally means like, you're merging and then going up from there. So in order to avoid ambiguity, you just do it in order of merges from left to right.
Yeah, Yeah, I got this. And then for the clusters, the 3 clusters, what did we get, guys? So we want 3 clusters. I'll do it in blue. So we kind of split it here. Does the height axis have to be to scale? Yeah, I would do this to scale. Let me.
It never says it has to be to scale. As long as you label the points, it should be fine.
I mean, yeah, I guess if they don't
It
give us
doesn't the
wet
question,
paper,
it doesn't say you have to draw out accurately.
Oh, right. Yeah, it just says label the heights clearly, right?
Yeah. So you can literally have like 20 next to 10, and it'll be fine.
As long as you make it clear that that's where the.
As long as you make it clear what value points to what. And I think it actually would be clearer if you only wrote in the values that correspond to a height of your dendrogram rather than making that like a proper scale, because then people can just see like the position of the height of each one and then just look at the values you've put in on your height axis instead of trying to work out where each one points to.
Yeah. Okay, so are these the clusters we got, guys? Same as this?
Yeah, I got that.
Cool. Awesome.
I don't think we have to put 17 in the curly braces.
I mean, it is a cluster of one element.
I think you still do because it is a cluster by itself. Yeah. So.
Fair.
Assume they want a cluster. Okay, so this is the 3 clusters the dendrogram would give us. Was there not the part B? There wasn't there yet? Okay. Now use k-means clustering to cluster the data set. So how I did this is, let me paste in my. There is a slight mistake on here, which I will fix. This should be 17, 25, 27. But this is what I got with my k-means clustering. So I started with these centroid locations, so 7, 8, and 25. Computed all of the distances from every point to that centroid, and then circled whichever centroid each point is closest to. And then I worked out the average. So the average of this 7 is just going to stay 7. The average of all the points closest to the 8, so the 3, the 8, and the 11, is just 7.33. And then the average of 17, 25, and 27 is just 23. And so these are the centroids after 1 update. And after 2 updates, these were the centroids. And these are the points assigned to the centroid. So these 2 to centroid 1, these 2 to centroid 2, and these 3 to centroid 3. And I believe it just said... Oh, right, yeah. And then because the assignments didn't change from here to here, that's how we know our algorithm's sort of complete. Even though the centroids changed, we know that these centroids will just sort of stay how they are. And so these are the 3 clusters I got for k-means. Okay, let me check Danny's. Oh, that's not okay. Yeah, cool, Danny. I think that's what I got to. So centroids 7, 8, 25 are initial centroids, and then we work out the new clusters, new centroids, and then we refit the data to those new centroids, and then we work out the new clusters again. And these clusters are the same as the previous iteration, so that's how we know that the algorithm terminates at that stop. And so k-means gives us a different clustering result to what our hierarchical clustering algorithm got us. Cool. I'm just a bit worried that this is taking a few seconds to save because it usually crashes everything after. Let me just mark those. Are there any questions about that? How do you calculate the new centroids? So you look at all of the points in a centroid, like all of the points assigned to a centroid, and you just calculate the average. So for example, after this first step that I've done, where I've... Oh, okay. So for example, Shay got 3 instead of 5. Oh, for what? Why did I get 3 instead of 5? The cluster is the same as the 1.5 for the 9.5 cluster. Oh yeah. What have I done there? 9.5. This is the distance. Top table distance between 8 and 3. 8 and 3. Oh, right. Yeah, that should be 5, shouldn't it? But everything else, I believe, is the same. Well, where Shay got 0.5 here. Yeah, this should be 0.5, I believe. Wait. 378. Oh no, yeah, I got that wrong. That should be 1.5. Yeah, okay. Yeah, so Danny's is correct. Mine is a bit weird. But yeah, awesome. To calculate the new centroid locations, so we look at all of the points assigned to that centroid. So say, for example, in this first iteration, this 25, we've got this, and this assigned to that centroid because they're the closest ones. So we take these three numbers and we just work out the average of these three. And that's where our centroid moves to, which is this 23. So we look at all of the points that are assigned to a centroid and work out the average of those points to work out the new centroid location. Does that make sense? Right. Oh no. Sorry, I'm getting a bit carried away. Okay, cool. I believe that's everything in that question. Question 1. Okay, question 2. Supervised learning. Often in practice, the attributes of a dataset are normalized or standardized in a pre-processing step before running a classification or regression method. Give one example scenario of a classifier or regressor where you think this pre-processing step is important, and one example where you think it is not. Justify your answers. Okay. What did we put for this, guys?
I can read out my solution if you want.
Yeah, sure.
Okay. So the nature of the data in some features may mean that it spans a disproportionately high/low range of values compared to the other features. This could cause a model to treat that feature with a bias/different level of importance with respect to the other features, leading to a lower accuracy. An example where this would be important would be a regression model trying to predict the surface temperature of a planet given the features distance from the sun in meters and atmospheric CO2 percentage. The distance value would range in the trillions of meters, whereas the CO2 concentration could only be a value between 0 and 100%. This would lead to it disproportionately affecting the model. An example where this wouldn't matter is a regression model predicting house prices based on features of distance to various amenities, such as shops, schools, parks, etc. This is because the data is likely to be in the same ranges as each other in most cases, and one would not be treated with much more importance than another.
Cool. Yeah, that's pretty much what I put. Do you want to send a screenshot of that and I'll paste it in?
Alright.
I just put this pre-processing step would be important if we're trying to model how, for example, an adult's age and a weight affects their income. They're both going to be in completely different ranges, which I think is what Adit was getting at as well. WCSS is not normalized, so Elbow method. I don't think that's what this question's getting at, Danny, but I see what you mean. Oh, right, yeah. No worries. So, yeah, for example, if we have if we have something like ages ranging from 18 to 101, and then we have incomes ranging from like $0 up to, I don't know, let's say 500k, then these two are in completely different ranges. And so if we do something like KNN on this, we're going to think an 18-year-old on 20k and an 18-year-old on 600, or let's say 500k, are much closer together than an 18-year-old on 20k and a 19-year-old on 20k. We're gonna value this. Actually, is it the other way around? We're gonna see these two as more similar than these two. That's probably not the best example. Okay, let's say we have 18 on 21k. Okay, we're going to see these two more similar than these two, whereas we might want to weight it equally. And so the idea is we want to squash everything down so that it's in between 0 and 1. Also that it's standardized, so it's got a mean of 1 and mean of 0 and a variance of 1. Either way, we're squashing everything down so that it's sort of in the same range. So this was my answer. If anyone wants to send their sort of responses, I can also add that to the document. The dental pattern weight thing between different animals. Okay. Yeah, that sounds like a good example. Is that to prevent any variable? Yeah, exactly, Ash. So, prevent any variable from dominating the distance metrics. Good point, yeah. So, for example, with something like the Euclidean distance, we want it all to be sort of weighted equally. We want to value every attribute equally. Cool.
I have one question about like feature scaling, if anyone gets it. It's that if in the model we assign the weights for every single free parameter anyway, because the model is given by like W0 plus W1, then the X1, W2, X2. So we assign a weight to every single parameter anyway. Wouldn't that like scale each feature to its corresponding like correct level of importance?
Yeah, so in a model like that where you wouldn't really need feature scaling, it's just in terms of things like KNN where we just have a single distance metric for all of the attributes, and we've not got any weights or anything there. Because obviously with a like linear model, we can just stretch basically the line a bit more or change the intercept or whatever to make it fit.
Okay, I see. So it's for like KNN and stuff where you don't really have a model with weights that can be adjusted.
Yeah. With saying that, I think it's probably a good idea to maybe mention, because it's saying give an example, so maybe we could say something like KNN. Make it clear that it's specifically for those types of algorithms.
So would examples involving regression, like how we did, they wouldn't be valid, would they?
I wouldn't think so.
Let me see.
Everyone just drop your thoughts. But yeah, I can still explain. Yeah. Okay. So yeah, all we're saying is we want to pre-process. We want to squash all the attributes down so we don't value one attribute a lot more than another attribute. We want to value them all equally. So for example, age and income, we want to value them both equally. We don't want to say the income is much more substantial than the age or other way around. Yeah. Yeah, exactly. Okay, let's look at question 2b. If I can find it. 2b. Okay, this was quite an interesting one. I saw quite a few people send messages in the teams about this question.
It's saying feature scaling is required for linear models and like any models as well.
Why?
Not just like KNN and stuff. So our examples would be correct, but I'm not sure like why. Oh, it's giving an answer. So in models with weights, each feature has a corresponding weight that adjusts the effect on the output. If it scales features very wide, if the scales of features vary wildly, okay, the model will need to adjust the weights accordingly, which can make the learning process more difficult and much slower, requiring much more computation. Oh, okay. Well, okay, right. So you need to do it for KNN, but if you do feature scaling for model-based algorithms such as linear regression, logistic regression, then it just makes the training process a lot quicker, which means
Right,
like
okay.
if you look at amortized kind of standpoint, it would probably be better overall to just
Scale it,
feature scaling
one
for
thing Victor
anything.
mentioned that I think I didn't mention is we also need to give an example scenario where it's not necessary. So I just wrote that it wouldn't be important for if we had one independent variable, because we could just
Yeah.
adjust the weights accordingly. So yeah, cool.
Or if you had like multiple variables in the same like range of values.
Yeah. And Danny's price of chocolate versus price of sweets. Yeah, so that's another sort of like linear example. We can always stretch that line. Cool. B. Consider the following two classification methods: logistic regression and k nearest neighbor with k equals 1 employing the Euclidean distance. Create and draw a 2D labeled classification dataset on which the leave one out validation error of LR of logistic regression is 0, but the leave one out validation error of one nearest neighbor is maximal. Right. Okay. How did we approach this? Does anyone want to? If LR is 0, they are linearly separable. Yeah, so if the logistic regression error is 0, then that must mean that we can linearly separate the data points. Is it not sigmoid curve? No, so the sigmoid curve is after we like deal with it. So something like this would work with a little logistic regression, and we could have a 0 error. The idea is we can separate it by from line. The only difference between linear and logistic there is the fact that we have a classification. Okay, Frantis sent an example. So from the inputs of the sigmoid curve, we produce a line. I believe so. When do we get the sigmoid curve with logistic regression? So the sigmoid curve is going to look something like this. Okay, that was not good. This is like the sigmoid curve. And then we take in some value of x and we predict the probability of it holding some property. So if it gives us a value of, say, 0.1, then it's 10% chance of this. If it gives us a value of maybe 0.7, it's a 70% chance of the property holding. So the sigmoid curve is just a way to turn a linear regression sort of thing into something which returns a number between 0 and 1, which we can then use to say yes or no, basically. Something which can then be converted to a binary output by just rounding it. Okay, we've got quite a few solutions. So Victor has sent something like this, and then we have this, and then we have this line of linear separability. Let's take a look at this. So during leave one out, the 1NN will always assume the wrong class. Oh, okay. Are these like closer than they are next to each other, like this? It has to be, yeah. Okay, let me. Okay, so I think Victor's got something like this, right? So they're linearly separable, but it's just the idea that these would be clustered wrongly because, say we're putting this X here, it will look at the closest one as a red dot and say that's the closest, so let's make this a red dot. And so these are sort of paired together when we're doing that 1 and n. But when we're doing that logistic regression, we can just separate it linearly like that and classify them all correctly. So the LR error will be 0, whereas the 1 and n error will be maximal, because no matter what point you choose, all of them will be classified wrongly. That's one example. Let's also get some more examples on here. So Ollie's done something quite similar to this, yeah. One that Franta sent earlier was something like this. So we have this. I think that would also work, because obviously it's linearly separable, but both pairs would be classified wrongly. So that's another example of where it's got a maximal 1 and n error, but a 0 LR error. Does that make sense to everyone? Cool. I mean, the main reason, Ash, is because it's a linear and parametric model. So we can represent those sort of, like, if there is 0 error. So the horizontal gap is larger than the vertical gap. Yeah, Danny. Okay, we'll come back to that, but yeah, I think Ollie sent a good link. Question 3. Okay, that's everything in question 2, right? I can delete this page now. Cool. Question 3. Search strategies. Tic-tac-toe is a common game played between 2 individuals. In this 2-player game, players play in turns by marking the spaces, either with an O or an X in one of the squares of a 3x3 grid. The condition for victory is to place 3 of the same marks in a horizontal, vertical, or diagonal row. A draw can happen when the victory condition is achieved and all the squares are full. This problem can be formulated as a search problem as follows. And it's given us what we need to find. So an initial state is given to us. The actions we can take is placing an O if the last action was an X, placing an X if the last action was an O. From the top left square, then the top middle square, then row by row, following that same pattern. Nodes are identified by the arrangement of O's and X's in the grid, and the cost of each action is 1. Always avoid loopy paths. So, A. Generate the depth first tree until the goal node is found. I can show you guys how I sort of approach this question. Let me... Okay, so I did this. I said our initial state is the one the question gives us, which is this one up here. And I just sort of created this key where if I write P and then S, comma I, that just means I'm placing the symbol denoted by this S in whichever cell has index I. And by index, I'm referring to this sort of template for the numbers. So P00 or P00 means I'm placing an O in the cell with index 0. So an O here. P02 means I'm placing an O in index 2. And so I expanded the 4 possible children of this node where we place an O in either here, 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 or here. And I got these 4. And because I believe it was a DFS, yeah, depth first search, I then looked at this node and expanded this into these 3. Obviously, there's only 3 things. Doesn't the question say that you place an O in the top left? Yeah, so that's what I sort of did here. This was our initial state, so I started with placing an... Why did you expand them though it's DFS? Ash, I didn't expand these, I just visited... I mean, I didn't... All I did was just write them out, so I've not actually expanded them. We still have to visit those possible solutions, just because writing out, like... Do we not?
You've written them out because they're on the frontier, basically. You didn't visit them. You expanded the initial node, and then that gave you all these neighbors. And you've done that throughout. You've just been expanding the leftmost one, which gives you all the neighbors. You haven't visited and expanded the ones to the right, though. You've only expanded the leftmost.
So these are just in the frontier, but I've not expanded them.
Yeah, they're just in the frontier.
Yeah, so first I place an O in this top left. Yeah, just like the possible sort of children we can reach, basically. Oh, it's... okay, cool. Yeah, so expanded this, and I expanded this into these three. And got these three where I place an X either here, here, or here. And that gets us these three. And then from this, I then expanded by putting an O either here or here. So that's these two children. And then finally, last move we can do is place an X here, which gets us to this goal node, where X has won the game. In terms of the solution for part B, the solution is the sequence of actions we take to get from the initial state to the goal state. So this is our first action, followed by this, then this, then this, which I've put here in a, I've listed them out. And the cost, we're told that each action costs 1. So it's just 1 plus 1 plus 1 plus 1, which gets us a total cost of 4. Does that make sense to everyone? Cool. Isn't the goal node with the winning X line on the left? No, not based on this. How did you get that there? No particularly. No, but Kieran, I think it says always start placing the marks on the top left square, so we have to do it in that order. So it wouldn't be possible to get the X on the in the actions it says yeah exactly. So we'd have to place an O in the top left square first if there's a free spot there. If there's not a free spot, then we look at the next sort of first available square in that same order. But yeah. Cool. Okay. Shall we move on to question 4? We good? Yeah. Question 4. Optimization problem formulation. Consider an illustrative problem where you wish to allocate n contractors to m tasks in a project. Does anyone want to talk us through this? Let me get what I put, but if anyone wants to come up, feel free. Don't appreciate the quacks. Okay, so why is this an issue for the problem? What did we put? Copy the constraint. Yeah, so it's not making sure that every contractor has at most one task and every task has one contractor. So yeah, I think this is just the exact same sort of issue as that last paper, but we're just missing the constraints. So for A, why is this a problem? We aren't checking for each task to be assigned. I'm going to type this out. We aren't checking that each contractor is assigned to at most one task, and we aren't actually, in terms of each contractor being assigned to one task, that's fine because the X vector can only store one value. So we aren't checking that each task is assigned to one and only one contractor. So we're not checking for that constraint. In terms of each contractor having just one task at most, that's fine because X is just storing the task numbers for each contractor. We can't store like 2 numbers in this slot. We can only store 1 task number. Having 0 contractors doing 0 tasks. I mean, I'd argue that oh right, yeah, so we're not checking that each task has been assigned. Yeah, good. Okay, so in terms of an adjustment, what would be the constraint we introduce? The one from the other paper. Okay.
Is it possible to write constraints in like words? Like, how would you say like every value in X needs to be unique?
I mean, how they did it in the other paper was something like GJX equals sum of... Well, they introduced that new thing called I, right? They said
the constraint in the other one was like xi is equal to j or something like that.
Yeah.
For every single value of j or something like that. Yeah.
So xi equals j equals 1 if...
But how would you write mathematically that you can only include each value of X?
Yeah, so what they did last time was like the mathematical thing. So sum of... And then they checked every task, so... J... No.
Oh, double for loop, okay.
Yeah.
That's what Victor's just put.
Let me paste this in.
Yeah, W Victor.
Cool. So we'd have a sigma, and we'd make sure that the sum of all of the contractors assigned to that task is 1, which means there is at most and at least 1 contractor for every task. And this constraint would basically do that.
So even though we're not actually looking at the product, like the result of the summation, we can use it like a for loop, can't we?
Yeah, basically. I think that would work, Danny. Equals the number of occurrences of I in X, and that it would have to be equal to 1, Danny, though. Yeah, because every task has to be assigned to exactly 1 contractor. We can't have any tasks that are assigned to 0. But yeah, that would also work, I believe. Awesome. Any questions? I made it to the Texiland solution PDF. Oh, Victor, I need to put your name on there, don't I? Victor. Victor the go.
Let's go, Victor. Your name is now forever etched in the server.
We've got to make our own version of PMT.
Nah, we've got to sell these to like the first years next year. That's what we've got to do. It's a business. It's maximum profit, I'm telling you.
Can you go over it real quick again? Sure. So, okay. Right. So we don't have any constraints, meaning that there's in the problem we're told that every contractor or every task must be assigned to 1 and only 1 contractor, whereas based on this problem definition itself, we're not really enforcing that in any way. So the way we enforce that is by adding a new constraint. And this is the constraint we add. So we say A equals B is 1 if A is equal to B and 0 otherwise. So we're just saying this new constraint is that everyone, so we add up all the contractors assigned to a task, say 0, and if there's 2 people assigned to task 0, this constraint won't be met. And so it's not a feasible solution. Whereas if this is equal to 1, that means only one contractor is assigned to the task. We check this for every single task and make sure there's only one contractor assigned to every task. This sigma is just counting how many contractors are assigned to that task. And we make sure that for all values of j, so for all of the task indexes that are between 0 and m, the number of contractors is 1 for that task. Cool. I'm going to stop that recording. Cheers.